Hi everybody, here we're going to go over the instructions for the refraction laboratory experiment. So let's go ahead and take a look at the outline for the lab. So we're going to skip part A and you're going to do part B and part C. And so there are also going to be two links for this experiment. So the first link is going to be the actual experiment, and the second link is going to be where you're going to look up some values for the indices of refraction. So let's go ahead and begin. So you're going to go start at section 8, and there's going to be some data to record. So for part B, section 8, you're going to go to the link, and you're going to, so here the experiment is going to run continuously, so you're going to hit pause, and you're going to read the instructions, and you're going to set them, these materials here to specific materials. I'm just going to change mine so that you don't get the same thing. I'm going to leave mine as air and water. You'll read the instructions. You're going to have to set your materials to different settings, but I'm going to leave mine as air and water. And so what you'll do is, so here this is the air is coming in. You can, if you click here on switch placement of light, here the light sources starts on the water side, and here the light source starts in the air side. So for the first part B, what you're going to do is keep the light source on the air side, and so this is going to be the incident side, and this will be the transmitted side. And then so what you want to do is you'll go over here, and you're going to select the material, the incident material from the list, and then the transmitted material from the list. So for you, these materials will be different. You'll just have to read instructions to specifically see which ones you have to do. And then once you have those materials set, then you're going to go to this wiki site here, and you're going to look up the indices of refraction for air and for water. So water is over here. It's going to be 1.36, and air, I'll let you look that up because you're actually going to have to do air yourself. So this is going to be for me, for water, 1.36. And these will be the theoretical indices of refraction, and you'll just have to record those. I'm just going to put one here, just to show it. And next, what you do is they're going to resume the experiment. So you'll go back to this link here, and you're going to resume. And what you have to do is for each corresponding incident angle here, you're going to record the corresponding transmitted angle. So probably the easiest thing to do, since this thing is going to continuously run, is to just pause it near the number, really near any number. So here, this looks like it's going to be about 14, I believe. So then this is going to be for 14 degrees. And even though normally you want everything in that size, we're going to keep these angles in degrees. And you're going to record the corresponding transmitted angle, which is going to be this one over here, which is about 10. And then you're just going to complete this table. There's no set values for the incident angles. You just have to read, and you're going to make 8 different measurements. So you just have to take 8 separate measurements of the incident angles and record the corresponding transmitted angles. And then you'll complete this table here. And the next thing that you're going to do is you're going to calculate the experimental index of refraction. So here, this is a theoretical transmitted index of refraction. Here, what you want to calculate is going to be the experimental index of refraction for the transmitted material. And the way that you're going to do that is you're going to go up here, and you're going to use Snell's law, plug in the given values for incident index, incident angle, and transmitted angle, and you're going to use that one to solve for the transmitted angle. You're going to use that to solve for the transmitted index of refraction. That's what you want here. And then so once you do that calculation, you're going to put that value here. And then you're just going to repeat the experiment for each of the corresponding pairs of incident and transmitted angles. So for this one and this one, then you're going to calculate the corresponding index of refraction for trial 3. And so on for all these other ones here, all the way down to trial 8. And this column here, this is just going to be the average of these values. And you'll conclude part B by first taking the percent difference between the experimental index of refraction of the transmitted material and the theoretical index of refraction of the transmitted material. This one over here. And the final thing for part B is to calculate the error for your index of refraction. And since here, this is going to be, you'll do some statistical analysis, this is just going to be the standard deviation of the mean of these indices of refraction here. And then that's going to conclude part B. Part C, it's a similar, well, it's the same link, but you're going to modify the setup some. So for part C, and actually I'm going to change it to another material to try to make it more extreme. Let's take diamond. Okay, so here the index of refraction is air. This side is air, this side is glass, diamond. So what you want to do here is we're going to study total internal reflection. So what that means is that, first of all, like for fiber optics, light, it starts off inside the fiber optic. So here you want the light source on the more opaque, optically opaque material, which is going to be the diamond. So you'll change the diamond, the position of the light source to put it on the diamond side. And you're going to look for a specific angle. So here the light comes in. This is the incident light. This is the reflected light beam here. And then there is also a transmitted light beam here. So the critical angle is going to be the angle where no light gets transmitted to the other side. Another way to say that is that the critical angle is going to be the angle on the incident side, where the transmitted angle is going to be 90 degrees. The end result, though, is that there's going to be a special angle where you're going to see that no light gets transmitted to the other side. So if you just run this, so you can see right there, the light beam disappeared on the transmitted side. So that's going to be the angle that you want to find. So you just have to kind of wait for it to come back. So as it comes back, there is going to be an angle where now the transmitted angle is going to appear, or just when it appears. So I'll try to see if I can get it myself here. So this is going to be around right there, about 27 degrees, 26 degrees. So that is going to correspond to the critical angle for diamond. So we have to do something similar here. So let's see again here. So around when it gets to about 27 degrees, you see right there, the light beam disappears. So this angle is going to be the critical angle for diamond. So for you, you'll have to do something similar, but with a different material. And then so here you're going to record, again, the incident material. In this case here, the incident was diamond. You're going to record you'll go to the wiki link and look up the index of the transmitted, the index of refraction for diamond. I'll just put a number here myself. I think it's 2.7. I'm just doing this from memory. And you're also going to record the transmitted material, which in this case will be air, and then the index of refraction for air, which I'm just going to put as 1. And you're going to record the critical angle, which looked like it was about 27 degrees. And here, since you kind of have to eyeball it, you're going to do this 3 times just to try to get a best estimate. So let's say, one case is 27, the other case is 27.5, and 27, let's say 26. So you're going to repeat the same experiment 3 times, and then you're going to calculate here for the calculations the average of these critical angles. That's what's going to go over here. And you're also going to calculate the theoretical, or you're going to calculate the critical angle using a theoretical formula. So here, it's still going to be Snell's law, but in this case here, what happens is that the transmitted angle becomes 90, so the sign disappears. And what you're going to have to do is to solve this angle for theta critical. And once you solve that angle for theta critical, then that's going to go over here. And you'll complete the experiment by taking the percent difference between the theoretical critical angle and then the average experimental critical angle. And that'll complete the refraction lab.